Before we look at the code, I will go over some background on how type systems work and, more importantly, how the constraints in the Hindley-Milner type systems are generated and how they're solved. So, in general, the idea of type systems is that you write these typing rules. If you write it formally, they look something like this, where we say, given a typing context gamma, the expression E has a type tau. And the context gamma is where all the variables that are available in scope will be stored. So the context gamma will contain all your x's and y's and so on and their types. And if I then have an expression x plus y, I can derive that its type is going to be, for example, an int. If x is an int, y is an int, and plus is a binary operator. So type systems are specified using these rules. And interestingly, you can think of type inference as one of the possible cases of this very general problem where we know some of these things and we want to figure out the rest. And it turns out that they actually give us quite a lot of interesting options. The most basic thing is we know everything. We know gamma, we know E, we know the type tau. And we just want to check that there really is a typing derivation. So the problem of type checking is we have all the information and we want to check that everything actually matches correctly. This is relatively easy, although even here, if you have some more tricky rules, it can get complicated. The problem that we are solving is the second one, where we know the expression, we also know the variables, and we want to figure out the type. And we don't want to just figure out any type because sometimes there may be multiple different types. And we want to figure out the most general or the best type that is applicable to as many situations as possible. Interestingly, you can also imagine a third problem where we know the variable context, we know the type we want, and we want to generate the program. We want to generate the expression E. This sounds quite weird, but it is something that actually exists, and the term for it is program synthesis. And it is not common in languages like ML, but it's something that actually works in dependently typed languages where if you have a very precise type, you can often synthesize an expression, at least for some small parts of your program. I said that we want to infer the best possible type. Formally, this is called the principal type or the most general type. And it means that you have a type, you infer a type for an expression E, and the type is the most general, the principal type. If for any other type that you can also infer, any other type that is a valid type of the expression, that type is a special case or subtype of our principal type. And you can sort of see this in some of the examples that we looked at, where, for example, I inferred, or F# inferred, the type of twice to be sort of alpha to alpha, and then the result was alpha again. In principle, it could infer a more specific type. If we force it by a type annotation, then we get a type where the function is just string to string. And this is a more specific type, which makes it less useful because it only works for one of our examples. Similarly, if, for example, we or F# inferred that the type of map is not A to B, but A to A, this gives us type that's more limiting. Our previous example still works. But if we, for example, then converted this value to a string, then that would no longer work because that's not A to A. So the type inference mechanism in F# always tries to infer this most general type. And the Hindley-Milner type inference algorithm does actually do this. It produces for ML language the most general type. This is something that in a language like F#, where there's more stuff, gets a bit more complicated. And there's sort of other things in F# that complicate the Hindley-Milner type inference, like you have types that correspond to .NET classes and they have members, or you have interfaces, which then means there has to be some support for subtyping. All those things get a bit trickier. And there's a couple of other approaches to type inference. One interesting popular approach is called bidirectional type checking, where it sort of combines checking and inference. So you have to specify some types, and then it can infer the rest of the types for you. And it's kind of an interesting trade-off if you want to have a more expressive type system. So let's have a look at the Hindley-Milner type system, and specifically how the constraint generation and solving work. So what we're going to write in for TinyML is a two-phase process where you give us an expression, we get an expression of the sort of same structure that we had in TinyML earlier. We analyze this expression, and from that we generate a set of constraints. So we walk over the expression in one recursive function and collect a bunch of constraints. And then we take these constraints, we pass them to a solver, and the solver will generate some substitutions, which is basically the solution for our constraints. And then once we apply these substitutions, we will get the inferred types. And in TinyML, we're going to do this in two steps. So one phase is going to be generation of constraints, the other is solving. The original algorithm by Milner, called algorithm W, actually combines these two aspects together. So it's a bit more difficult to understand because it contains both the constraint generation and the constraint solving in one step. And to make our life a bit easier, we're going to split these two. We're going to represent constraints as using F# data types. So these are the key types. We have a type that the type that's called type, which represents our types in ML. And we have a primitive type number. We have type variables. I'll explain that in a second. And we have functions, which is sort of type of the input, type of the output. And we will support lists as well. So we have a list of type that represents the sort of elements of the list. Now, type variables are these sort of tick A, tick B, and so on, or you can think of them as generic type names, type variables. They will just have some name. So a variable is a variable of some name that represents an unknown type. And what the type inference is doing is that it generates these type variables, and then it produces constraints that it can solve. And once it solves the constraints, some of those type variables will become known fixed types like ints. Some of them will remain unconstrained, and those then can be treated as polymorphic. So a constraint really is just a pair of types of this form that says, like, this type has to be the same as the other type. And there's some of the constraints will be very easy or quickly, obviously impossible. If we say int has to equal a function int to int, that's not possible. There's no solution. Your program is not well typed. If we have int list has to equal int list, the two types are equal, so the problem is immediately solved. The more interesting cases are when there's variables involved. So if we, for example, say a variable a is int to some variable b, this is a constraint where we now have to figure out that actually a has to be a function that takes an int and returns b, or if we say a is a C to int, we are constraining a. It cannot be any type, it has to be a function. So the way the actual implementation works is that we will first walk over the expression that represents our program. We will annotate it with types, but all those types will be, or most of these types will be type variables. And we collect constraints on the side that represent the constraints on those variables. And as we are doing this, we will be generating fresh type variables. This means type variables with new names that we have not used anywhere else, and put them in the places where we don't yet know what the type will be. So if you say let x equal something, we will just generate a new type name, new type variable called a, and then some number. We put in the typing context this new type variable, and when you then later on access x, the system will know that it's the same type variable. And if we later on resolve the constraint and figure out that a, this weird number, is an int, we will later substitute the actual type for the type variable in the expression, and we will have the real type. So the constraint generation part is relatively easy. The more interesting bit is where we solve the constraints. And I want to give you just a quick example illustration of how the constraint generation works. So I'll do this using a sketch, and then I will later on look at implementing a bit of code that actually does some of the solving, but I'll leave the interesting parts to you. So as an example, let's look at this function, which is an expression that represents a function taking x as an argument and returning x plus 1. When we start analyzing this code, we will look at the expression. This is the lambda function, and we know it takes x, but we don't know anything about its type. So we will annotate x with a new type variable, let's call it a. Then we will continue by looking inside the body of the function, and here we have a binary expression, and all we are going to do first is continue recursively. So in the left branch we have x, and we previously assigned the type variable a to x, so we know this is some a, and we're going to look at the right operand, and this is a number, so we do know this is a type int. And now we also know, sort of from definition, that the type of plus is a function that takes an int, takes another int, and returns an int. And so this is where we can start generating some constraints, because we know that the arguments of the plus operator, the inferred types, have to match the types that are required. And we do this for both the left and the right branch. So on the left, we have a constraint that says a has to equal int, and symmetrically on the right, we will have a constraint that int has to equal int. This is a trivial constraint, but we generate it anyway. And now we also know that the return type has to be an int. So the body of this function, the return type will be an int. We know that because that's what the plus tells us. And so the overall type of this function that we can now infer after we've looked at the body is that this is a to int. Now, this is what the constraint generation will do, and later on when we solve the constraints, well, int to int, this is going to be easy, and once we solve the a constraint, we will know that a actually has to be an int, and if we then, once we've solved the constraint, substitute our result into this final expression, that we will know that really the type of this function has to be int to int. And this was a relatively simple example, but let's have a look at something more interesting. And I will not try to do the constraint solving here, will not show you the final resulting type, just go through the constraint generation phase, because that's what I'm trying to describe here. So what is this? It is a function that takes an f, the body is then another function that takes an x, and inside this nested function there's a conditional that says if x equals 0 then what? Then 0, otherwise called f of x. So just like before, we start by looking at the topmost expression. This is a lambda function, and we know it takes some f. We don't know anything about this, so we give it some type A. And then I can actually write these sort of the variable context here on the side, because there will be more things in it. So we know f, the variable, is of type alpha. And then we continue. Again, we have a new variable. So we generate a new fresh type variable for it, and we'll see later on if that gets constrained to something. And now we are inside the conditional. So in the conditional, again, we will sort of proceed recursively to all its sub-expressions. There's 3 of them. The first one is the one that says x equals 0. So I will continue recursively further until I get to just x. And here I'm accessing a variable. From the variable context, I know this is of type B. And 0, I know this is a number, so that's a type int. And again, equals is some built-in operator where we know the type of equals is int to int to int. In reality, in F#, equals is polymorphic, so that would make it a bit more complicated, but we're just going to do a non-polymorphic version here. And so if we know equals is a int to int to int, oh, sorry, this has to be bool. So we have to return bool. And if we know the 2 arguments of equals are both integers, that means we can generate some constraints. We can generate a constraint that says b has to be an int and int has to be an int. And then the result type of the equals operator is a bool, so we can use it here and we know we got a bool. Then we continue into the 2 branches. So 0 is an int, that one's easy. And what is f of x? Well, that's some function application. So here we have to look at f and we have to look at x. Now, this is going to be a bit more interesting because when we look at f, we just know this is some a. And when we look at x, we know this is some b. That's just the type variables that we assigned to these 2 things earlier. But now we have a function call. So the argument of the function has to be compatible with the input type of the function. And so far, f is just of some type. We don't look inside. We just say we got some type here. But we know this has to be a function. And so what we're going to do is that we're going to say, well, the type of f has to be some function c to d. And because the type that we got from the recursive call is A, this has to be the same as sum C to D. And the argument, the type of the argument B has to be the same as whatever this function requires. So this has to be B. When you're generating constraints for a function application, this is completely mechanical process, because we just invent some new C and D and say, well, the function has to be C and D, the argument has to be C. And then whatever we get from the recursive calls, we use in these constraints. And so as the result, we will say, well, now the result of this has to be whatever the function returns, and that's our newly generated type variable D. So this is what we get from the function application. And now we're back in the conditional, and there's still a few things that we have to do with the conditional. So when in conditional, well, there's one trivial constraint, which is that the condition has to be bool, and if we're doing this mechanically in our algorithm, we just say, well, whatever we got from the recursive call, whatever type of that expression was, that has to be a bool. So we're going to generate a constraint for it. And yes, when I'm doing it on paper, I can see that this is true already, but we're going to write it anyway. And then the other constraint is that the types of the things that are returned from the two branches have to be the same. We got int and the D, so we're going to add a new constraint that says int has to be the same as D, and the if expression returns a value of the type, that's the type of the two branches. And so that was our int and the D, and here we could just pick one of those two because we have a constraint that says int will equal D. So I'll pick the true branch and return int here. And so then I will sort of continue and say that this function, then the nested function, then has to be B to int. And the whole expression has to be A to B to int. Now, if we solve the constraints, then it will turn out that x has to be an int and f has to be a function int to int, but you sort of do that later on in the next step. So this is how constraint generation works, and you will write it yourself in the step-by-step tutorial, so you will see exactly how to put everything together. The next thing that we have to do, and we will look at this in the next video, is how you actually solve the constraints.